Oh, definitely come in person. Oh my gosh, no. If you have the option to go to a conference, go in person. That's the whole point of conferences.
I work at Snap on augmented reality. We do all kinds of things like computer vision, machine learning, graphics, and rendering on mobile in real time, all using C++. So please come to talk to me if interested. And as you can imagine, for this, we care about performance. And I'd also want to say a huge thank you to Sergey Huralnik and Eduardo Madrid, who I've had a great pleasure working with at Snap, who greatly helped me in preparing this talk and are much more experienced in these topics than I am. So if you have any questions, I'd ask you to remember the slide number. Oh, conveniently, this slide doesn't have a number, but you'll find it. And ask them after the talk, because we have a lot of material to cover. But if you won't have time, come find me after the talk, anytime at the conference or in Discord. So, as Tony Van Eert famously said at C++ Now 2023, people are not writing enough functions. And before that at CPP North 2022, C++ Now 2021, and also here at CppCon at 2017. And you know what? People are still not writing enough functions. So it's worth repeating this. But when people finally start writing enough functions, we'd prefer to get only the well-designed ones, right? Otherwise, Tony wouldn't be happy. And this talk will focus on this part, and specifically from performance perspective. But when talking about performance, we typically think about only the function logic and optimizing that part. But we'll see that a well-designed function API sometimes can have an even larger impact. So to start with, how will we compare performance? Well, benchmarks at this low level are not reliable, and they don't represent performance in large projects well. Because large projects do more than running a small piece of code in a loop. They do much more at the same time. But we'll do some benchmarks anyway, because people like them. Something like a dynamic instruction count is more reliable on modern CPUs. But we'll mostly use simple examples, so we can just compare the number of instructions the compiler gives us. And it should be a good estimate. And to give it a real-world context, there's an article, Accelerate Large-Scale Applications with Bolt, which talks about machine code of tens to hundreds of megabytes in size. And it says it's nearly 30% in many cases of processing time is spent getting an instruction stream from memory to the GPU. So if we reach our goal in reducing the number of instructions, we don't only improve execution time, but we also help the instruction cache. And now I need to make a disclaimer that our discussion will be relevant only for non-inlined functions. But does it mean that should you go to the door right now? Well, the official ISO C++ wiki tries to answer a question, do inline functions improve performance? And the answer is, it depends. And they say that they're often totally irrelevant to speed. And also, I'd like to say thank you to Khalil Estel, who allowed me to use this data from his slide yesterday, where he measured the Firefox function size distribution. And in there, we see that more than half of the functions are actually under 127 bytes, which is probably smaller than most people would expect for a non-inline function. So I think this is a pretty important case. Now, to understand how machine code is generated from your C++ code by the compiler, we'll need to follow this flowchart. At the top, we start from the C++ standard, but it doesn't cover all the implementation details. For that, depending on the platform, you need to go down to either C++ Itanium ABI, which itself delegates some parts to System 5G generic ABI, in combination with platform-specific ABIs for ARM, x86, etc. And on the side, we have Microsoft doing their stuff with Windows ABIs. So I'd like this talk to be relevant to as many of you as possible. So we'll include the following 6 platforms here. So the first, the left column, is ARM architectures, which are mostly relevant to smartphones and new MMX. And take a note that the second and the third columns actually share the architecture, but they don't share the ABI, and it makes a difference. So you see the same instructions there. So the middle column is mainly about Linux servers and older Macs. The right one is about Windows devices. And also the first column is mostly 64-bit modern architecture, so we'll focus on those ones because they're more relevant today. The bottom one is for like ancient devices and low-end Android devices. But we'll take a look at there when there's an interesting difference. And sorry, I don't have any experience with embedded, so I'm not a good person to talk about it. Maybe ARMv7 covers some of that. And to understand the code, we'll need to take a look into all these ABI specifications that I linked in the slides, and specifically the parts about calling conventions. And also here I mentioned the compilers used. Those are typical compilers for these platforms, which is Clang for the first column, GCC for the second, and MVCC for the third. So we also cover all the major compilers. But ultimately, in our examples, the compiler shouldn't matter because there's like no much place for optimization. So as you can probably see already, things are complicated. But don't worry, we'll be looking for some simple guidelines to navigate this complexity. And luckily, we have C++ core guidelines that seem like a good candidate. OK, so let's start with the return value. And indeed, we have a guideline for that, for output values, so prefer return values to output parameters. And they say something about self-documenting, but we don't care about this. We care only about performance today. So let's check this guideline for some simple but not too trivial type, like a unique pointer. And we have 2 options. One returns a null pointer by value, and the second one through output parameter. Now, a quick poll from the performance perspective. Who thinks these options are the same? OK, very few hands. Who prefers the return by value? OK, more hands. And output parameter? Yeah, people don't like output parameter. So let's see the results. And indeed, on all our 3 major platforms, we see that the output parameter produces more instructions. And what you can notice there is the call to operator delete, which wasn't present on top. So why it's there? Well, if you look at the code, it becomes clear. We pass some existing output parameter into the function. So it may be non-empty. So before setting something, we need to destroy that object. Yeah, but that's not all. When looking at the function, it's important to also look at the call side, because there are many more call sites in the code than just a single function. And for this example, I hid the definitions of our functions to ensure they are not inlined. Because, yeah, these are very small examples. They would almost certainly be inlined, but for the sake of this talk, it's better to have them to clearly see the difference. And we have 2 options, one calling our first function, and the second calling the second with output parameter. And looking at the result, we see that the second option produces way more instructions. And if you look just at the middle output for GCC, you would probably be confused. Because after the return instruction, there's some code and there's some jump to undefined label. But that's just a compiler explorer. You could tweak the settings to show like the full output of the compiler, but by default, it can hide something. But if you look into other columns, there's like a big hint what's happening. There's unwind mentioned, which means stack unwinding when an exception is thrown. So why is this in there? Well, in our second function, before calling function with output parameter, we need to construct this object. So it has to be destroyed if our function throws, because it's a local variable. So that part makes sense, and unique pointer has a non-trivial destructor. But after that, if we zoom in on the GCC output, there's still some difference in one instruction. For output parameter, it puts 0 into some memory. And again, if you look at the code, it's quite clear what's going on. The unique pointer must be default constructed before the call or constructed in some way. So for unique pointer, that's just setting it to 0, but for more complex types, you can imagine much more overhead in this place. And maybe you're thinking, maybe we can avoid it for at least trivially constructible types. But well, core guidelines ask us to always initialize an object, and I hope you treat initialized variables as errors in your code base. So that doesn't help. Oh, and yeah, just for the sake of slides, I did a quick benchmark, which probably is not representable, but for this simple case, the output parameter showed 25% overhead. So if your function gets more complicated and grows, it will go down to like 10, 5, 1%, but this overhead will still be there. And there were attempts to improve output parameters, like in this article. And then the final example is this deferred construction of an object which we then pass into our function. Well, does it solve our problems? Well, definitely it avoids the default constructor before the function call. But unless we fully trust the user to do the right thing and don't have exceptions at all, it has some issues. Well, stack and bind on exception is still necessary, and it took quite a lot of code, as you saw. And we also need an extra bool flag to know if the function actually initialized the value and not initialized it more than once. And actually, that's what the library actually does. So there's extra overhead, like an std optional. But guess what? Any C++ compiler checks that every execution path in a function ends with the return statement. All we need to do is just return by value. And we don't need this runtime flag. So at this point, hopefully that's enough evidence to convince you that output parameters is a bad idea. But now let's look deeper into how return by value works, and specifically for C++ abstractions. So again, core guidelines recommend us to use a unique pointer and say that it's the cheapest way to pass a pointer safely. So let's try to do this. Let's compare a function that returns a pointer, but the first one returns a row pointer, the second, the unique pointer. And let's take a quick poll. Who thinks that unique pointer adds some overhead in this case? Okay, some hands are slowly rising. Who thinks that there's no overhead? Yeah, I think kind of half and half. And what we see in the assembly that unique pointer actually added some overhead. And let's explain this. So first of all, what we need to know when reading assembly, things like x0, xr, eax, etc., are machine registers. And they're the fastest storage available on machine for your program. And when you see a register in square brackets like below, means that the register stores an address, and we're accessing memory at that address. And by definition, it should be slower than just using registers. But maybe you're wondering how much slower this is. Sorry, there's a question?
Yeah.
Please use a mic if you have a question.
Actually, this code looks like to me that in the upper row, everything is optimized out because eax is just set to 0.
No, it's an actual function body. So we return a null pointer, so all it does is returns a null, well, sets to 0. So yeah. So maybe you're thinking, how much faster? Well, I made a quick benchmark for this simple example, and it turns out it's 3 times slower. The output, when we use the memory, it's 3 times slower than the registers. And again, even if your function grows like 100 times, this overhead will still account for a couple of % of your execution time, which, well, depends on your use case if you can accept that. So returning to the core guidelines, well, maybe a unique pointer is indeed the cheapest way to pass a pointer safely, but unfortunately, it's not free. But so to understand this, why this happens, let's look at a more simple example and something more trivial, because unique pointer does some like memory management. It's complicated. So let's write a simple wrapper over just int, and you might think, why would anyone want to do this? Well, there are a lot of libraries that depend on this. First of all, well, the smart pointers similarly wrap row pointers. There's std, chrono, and other units libraries. By the way, at the same time, we have a talk about MP units. So you could tell people from there what you see on the following slides. It would be interesting. And also safe integers and bindings for other libraries. OK, so anyway, we're wrapping an int, and it's not like anyone can stop us, right? And in here, you can imagine like, a diligent person who explicitly writes down all the operations so that we can see there's nothing unexpected happening in there. And we try to use this wrapper as a return type to just return the number of seconds in a minute and compare it to int. And when we compile this code, well, again, we see those nasty square brackets which add overhead. And it may be confusing why. And it happens on all the platforms. So we go reading the Itanium C++ API, and it says that if the return type of a class type that is non-trivial, the caller passes an address as an implicit parameter. And yeah, we see this address here. That's exactly our problem. So, and then we kind of refresh our C++ knowledge and remember that trivial class is defined as trivially copyable and some other condition. Yeah, so this is what we're after. So let's make our class trivially copyable by removing the copy and move for good measure. And yeah, one way is just to delete them. A second way would be to default as we have in the comment. OK, we have no custom copy, good. And nothing changed. OK, we need to do more reading. So Itanium API defines a type as a non-trivial for the purposes of calls if it has non-trivial copy constructor, move constructor, and destructor. And yeah, that part was kind of non-obvious from the trivially copyable name, but now we know what to do. And by the way, just note it's different from C++ trivially copyable definition, which also requires trivial copy and move assignment. OK, we remove the destructor. And suddenly we're getting something, somewhere on, at least on the 3 platforms. The square brackets disappeared. OK, so at this point, we're thinking, OK, maybe we're onto something. Maybe just deleting more code will solve all our problems, right? So we delete the last thing we could, the constructor, and keep the default initialization to 0. And guess what? It helped on Windows, but not on x86. So at this point, it's time to dive into the specifications for the APIs. But don't worry about reading this right now, because I gathered the important part into this table for you. And the first thing you can probably see that, first of all, we're looking at only at composite types here because most fundamental types can be returned in registers. But for composite types, first of all, you can see there's a size limit on all the platforms, and it's quite different on them. And there are extra requirements for all of them. Well, we remember the requirement to be trivial, but also Microsoft API introduces a C++ or 3-pod requirement, which means no custom constructors at all, no private members, etc. And on x86, only fundamental types are allowed. OK? And by the way, core guidelines have this guideline to avoid defining default operations. If you can, this is called a rule of 0. And I guess after seeing our example, we can strongly approve it for performance reasons. And at this point, you're thinking, well, surely this problem is handled properly in all the popular libraries, right? Oh, right? Well, after seeing seconds in the example, I think you were expecting to see std chrono. And in here, we again return the same value, but in the first function as row int, and the second one is chronoseconds, and we check that the type is actually the same. It's int 64. And we put it into compiler, and we're good only on 2 platforms. And interestingly, the reason on everywhere is the different. So on MSVC, the problem that it's not a pod, because it encapsulates the value. On x86, it's just not a fundamental type. And on ARMv7, the problem is that size is greater than 4, and there's different handling for fundamental and custom types. So can we do something about it? Well, std chrono would have to give up any encapsulation to be maximally efficient on Windows. Not sure if that's reasonable. And it simply cannot use types smaller than int64 just to account for like one architecture, because the seconds may not fit in other types. Another fun example, so std pair. So copy and move constructors are defaulted. We're good here. But only since C++17, std pair can be trivially destructible. And if you were following along, you can see that it's an ABI breakage. Because before that, it could be passed only in memory. Now it can be passed in registers. But I did a quick Google search, and surprisingly, on the first page, I saw only one complaint about this breakage. And next part, copy and move assignment operators are trivial only on MSVC. And this is not a problem for the function calls, as we clarified before, but it's kind of a performance problem for memcpi and bitcast, which require this property. Oh, and the std tuple is a fun one. It's never trivially move constructible. I have no idea how that happened. So can we do something about it? Well, don't use a std parent tuple if you can. And a name struct is better for both code readability and performance for these reasons. And going back to our unique pointer example, I thought, what can we do? And the only idea is to manually extract the implementation into a separate function, which returns a row pointer somewhere hidden. And in the actual API, which hopefully is always inlined, we wrap it into a unique pointer. Well, but that's not great, a lot of manual work. And at this point, we actually have everything to talk about return value optimization, or as it's called, copy elision. So just to do a quick reminder, since C++17, a pure R value is constructed directly into the storage of its final destination, thus avoiding extra calls to move and copy constructors. And we actually already saw how it works under the hood. We already saw this paragraph in the Athenium ABI. If the return type is a class that is non-trivial, the caller passes an address as an implicit parameter. And the callee then constructs the return value into this address. And to clarify, it's passed as the first parameter into the function. So if you're using an output parameter, for consistency, I'd also put it as a first parameter. And if you think about it, it's actually exactly an output parameter, but done right for you by the compiler. And it's done only when necessary, when we cannot use registers, which would be faster. And on Monday, there was this great talk about RVO, which almost turned out into a battlefield. But it showed good examples of how you can mess up RVO inside the function. But our focus is different. We're not looking inside the function, only at its API. But I think we still can add something interesting to this. We'll look at the use case of inserting a function result into a container. And for such cases, it's useful to emulate some large struct with a struct like this with all the standard constructors declared but not defined. This way, in the assembly, we'll see which of them are called. And we have a make large function, which again we don't define to make sure it cannot mess up RVO for us in any way. And we put the result into std optional. And in here, we didn't do anything criminal on the slide, but we run the compiler, and in the output we see move constructor being called, destructor appearing 2 times, one in the stack unwind section. So what's the problem? Well, turns out we're using this std optional constructor, and it gives our parameter a name value, which turns pure R value into just R value, thus disabling regular RVO. And then obviously it forwards this value into the storage, which disables named RVO. So can we do something about it? Oh, and yeah, it affects basically all of it: constructors, and place, insert, pushback into all the containers, optionals, variants, vectors, maps, etc. So can we do something about it? First, I saw this solution in Arthur Dwyer's blog, which calls it with the return of t, which references this blog by Andrzej Kimienski, which calls it R value. Robert Leahy on the slides called this elide, and there's even a standard proposal with this name. But I most like the name used by Ivan Chukic, which actually used name lazy for something more complex, which also caches the value. But I think simple names should be reserved for simple things. So in my library, I added this simple wrapper lazy, which just stores the function, and the important part is this conversion operator into the function result. And at the bottom, instead of directly calling make large, we pass it as lazy into the optional constructor. Well, I won't dive into details why this works. You can read the article listed. But the idea is that we don't pass a value and instead the function. And this conversion operator is called only in the end, which enables RVO. And we look at the assembly, and indeed, all the unnecessary overhead is gone. We just have a call to our function and some optional stuff around it. And in here, I'd like to draw your attention to the fact that we're witnessing a specimen of a rare kind of negative overhead abstractions, which is also great to have. So returning to where we started, to our guideline, should we prefer return values to output parameters? I think we can heavily approve this. But also, it mentions that a reference could be either in-out or out-only parameter. So let's look into that. I think there are still valid use cases for output parameters, but mainly where the return value cannot be allocated on stack. For example, if it's a range with a runtime size. And we have algorithms like ranges transform and sort. And it makes sense if we decouple allocation from data processing, the code becomes more reusable. But a small digression, imagine you're a C++ newcomer and you see this transform call. How do you know which of the parameters is the output one? There are 3 options, and also for sort, do you know if the argument is modified or a new range is returned? So I thought about this problem, and in my library, I introduced some simple out and in-out wrappers, which currently don't provide any guarantees, but at least you can clearly put them into the function signature and also at every call site. And also, if you have sort, you can make 2 overloads, one which modifies the range in place, and the second one which returns a new one. And I think this makes the code more readable. Yeah, so that's the end of the first section. Let's take a very short break and continue with parameter passing. Okay, so again, we have a core guideline for this, which says for in parameters, pass cheaply copied types by value and others by reference to const. And by chip to copy, it says it depends on the machine architectures, but 2 or 3 words are usually best passed by value. So let's investigate this. Let's start with a simple example with just an int parameter and pass it by value by reference and do something simple inside the function. So who thinks that they're like, from performance perspective, they're equally the same? Okay, no one. Who thinks that pass by value is better here? Okay, most of you, and pass by reference, anyone prefers? No, good. So we look at the assembly, and indeed, when we pass by reference, we again see those nasty square brackets, which means others accessing the others. And in this case, I think it makes perfect sense. We pass a reference, so well, we need to dereference it. But again, when talking about function API, we need to also take a look at the call side. And for this, we just pass a constant 1 into both our functions. And what happens, so for pass by reference, there's much more assembly generated. And what happens, so at the top, you see just a constant 1 put into register and the function called, which is exactly what we'd like to see. But at the bottom, because we need a reference, we first need to put this constant 1 onto the stack, then take the reference, and after the function call, we also need to clean up the stack. And people like to talk about premature optimization or profiler-guided optimization. But for cases like this, I don't think any profiler will guide you here, because this code for calling the function, it's spread out across all the call sites, and likely a single one of them is never an overhead, which the profiler could notice. And again, I did a quick benchmark, and surprisingly, the overhead of using memory versus registers here is also like 200% as in the previous benchmark. But this may be not too representable. But there's another interesting thing. Most of our functions aren't as simple as we saw, and they call other functions. So we define some extra function to call, and in our example, we first make a copy of the argument, then call this extra function, then compare the copy to the input value. And I think it's obvious that this should always be true, right? Well, guess what? When passing by reference, the compiler, after the call to our function, it always has a CMP instruction, which compares the values. And on the top, it indeed returns true for us. So what's the problem? Well, when we have an opaque function call, the standard doesn't allow the compiler, well, standard forces the compiler to assume that this function can change any value, even though it doesn't take any parameters. And this includes the value referenced by our reference that we pass into the function. So we're forced to read it again and then compare it. And also, while we're here, it's important to talk about perfect forwarding. And from some definitions, the act of passing a function parameters to another function while preserving its reference category, which in practice, the main purpose is to avoid extra copies when we can call a move instead. And it's typically used in such functions like makeInic, which takes some arguments and simply forward it to the constructor of our type. But I'd say it's not perfect. The first part that we have forward here, which breaks RVO, but there is a second part. There's this forwarding reference, which is still a reference. So it actually prevents passing parameters in the registers. So if this part is not inlined, we'd get the problems we saw on the previous slides. So hopefully that's enough evidence to convince you that at least for built-in types, they should be passed by value. But now let's see what other C++ abstractions should also be passed by value. And no talk about overhead can avoid mentioning Chandler Carruth. And in here, he already walked over the example where we pass unique pointer by value. So we won't repeat this. But we'll just clarify from the ABI specification that if a parameter type is a class type that is non-trivial, the caller must allocate space for a temporary and pass the temporary by reference. So we still get passing by reference, but it's different than if we just pass the type by reference. Because in this case, as you see, there's a copy produced at the top of the stack. So as a conclusion, for non-trivial types, it's better to pass them by reference, well, unless you need that copy inside your function anyway. OK, now let's look at some interesting trivial types. And core guidelines heavily suggest us to use span. There's like 16 occurrences of this phrase. And it says something about errors, but we don't care about errors, we care about performance. So let's do exactly that and try to use span, okay? And let's implement some simple operations like a span back. And do this with the old C way, with passing a pointer and size, and then with std span. Okay, who thinks there is no overhead from span here? Very few hands. Who thinks there is overhead? Much more hands. Looks like I made you too pessimistic. What actually happens is on most platforms, there's actually no overhead. And on x86, I'm not sure what happened. Looks like the operations are the same. They're just split into separate instructions. So I'd count that as passing. But only on x64 MSVC, there is some overhead. But before explaining what's happening, let's see if we can break other compilers as well, or platforms. Let's take something more complex, like C++23 MD-span. And instead of using it directly, I emulated it with a simple struct so that we can clearly see that the data is the same that we're passing to the row function. OK, so we compile this code, and it breaks on 2 more platforms by having more instructions there. So what's the problem here? Well, again, we need to read the ABI specifications, and here are some relevant parts for this. But I gathered the important parts into the table. And as we see, for composite types, again, there's a limit on the size, which is often 16, but on MSVC, it's for some reason 8, which is a problem for std span, which has size 16. Also, we needed to add 1 more row into the table, because on x86, Microsoft provides 2 different calling conventions. And when using fast call, it allows to pass fundamental types in registers. Otherwise, it uses stack only. And on x86, only SIMD types are allowed. So again, quite a variety. So going back at the core guideline, well, should we use span? Well, you need to know that it's not free depending on the platform. But since I don't use Windows much, I guess I can live with that. Now, while we're talking about the type sizes, let's also talk about an interesting corner case like empty parameters. And there are surprisingly many use cases for it. All the predicates and transform functions that you pass into standard algorithms, they're often empty. Also, there is a use case of tag dispatch, which becomes somewhat obsolete with C++20 concepts. But the idea is you have different kinds of iterators, and if you have a random access iterator, then you can increment it more efficiently by just adding the offset instead of incrementing it n times. And there's another interesting use case, something like an access token to make some API available only to limited users, which is kind of like a default packaged private access modifier in Java. Okay, so let's imitate some tag dispatch, and suppose we're trying to improve std RAM by providing some kind of a customization for it in forms of a tag to specify which algorithm to use exactly. So the same functions, just the second one takes an empty parameter. And what we see when we compile this, well, on some architectures, it has no overhead, but on some, it does. And I tried to dig into this, and Itanium ABI specifies that for empty classes, they have size and alignment 1, but the ABI can override this rule. So it seems like the size 1 is exactly what MSVC is doing. That's why it produces the overhead. But I tried to look into ARM specifications, and I didn't find the part that would override this. So maybe I just didn't search well enough, or maybe it's some gray area in the specification. I'm not sure. So going back to the guideline that we started with, should we pass cheaply copied types by value? Well, I think we can approve this. The only thing that's confusing to me is where did they get this 2 or 3 words formulation, because in all the common platforms that we saw, it's either 1 or 2 words that can be passed in registers. But overall, the idea is totally correct. Oh, and also regarding parameters, it's important to mention another special case, which is this parameter in class member functions. And Itanium ABI says that non-static member functions take an implicit this parameter of pointer type, and it passes the first parameter. And immediately you see this is kind of a problem for small classes, which would be more efficient to pass by value. But luckily, right? Okay, it's not on the slides, but luckily yesterday I found out that actually C++23 introduces static keyword for the function call operator, which would help to mitigate this. It was on the other slide, sorry. So to understand what I'm talking about, the main effect is on the function objects, like std+, which is shown here. But of course, std+ would likely be inlined in most cases. But if you define some more complex operation as a function object instead of a function, you would get this overhead. And yes, C++23 provides a solution for this. Okay, so it's the end of section which talks about a single parameter. Now we'll talk about functions with multiple parameters. Okay, and let's start with this example. Suppose we have a sum function with 2 parameters, which we can expect it to add these values. And now we want to use it to add 3 values. And there are like different ways to combine the values, and mathematically, of course, the result is always the same. But for the practical purposes, what do you think is the most performant implementation for this? When we first take parameters 1, 2, 1, 3, or 2, 3. Well, let's vote for 1, 2. Okay, quite a lot of hands. 1, 3. No hands, and 2, 3. Yeah, there are some hands. It's nice. And just for the interest, I'll add another function into the comparison, which also uses parameters 1, 2, but swaps them when passing to the sum function. And I won't show the assembly because there are too many options. But we see that on all the platforms, consistently, we see that 1, 2 has less instructions than everyone else. And then the instruction count grows basically by 1, and except for MSVC. Okay, so let's explain. And if we dive into the assembly for one of the cases, which is GCC, we see that 1.3 option has an extra move before calling the first sum function. Okay, so why is it happening? Well, important thing you need to know is the order of parameters is fixed in every ABI. Or maybe more correct ways to say that the assignment of registers to these parameters is done in the specific order. So if we have some function with parameters 1, 2, they go into the specified registers for these slots. And the third parameter will go into the third register. So when we call the first function, in the first case, both x1 and x2 are on the correct place in the correct registers. So we can just call this function with minimal preparation. In the second case, x3 is not in the correct place, so we need to move it, which adds a one move instruction, which is exactly what we saw. For the third case, both of them are in wrong places. And in the fourth place, we have 1 and 2 in the correct places, but swapped. And I think everyone knows here that swap requires 3 moves to resolve. And this is like super consistent with the instruction count that we saw, except for MSVC. Don't know what happened there. And in here, I'd like to recommend you to watch this great talk by Eduardo Madrid, which was investigating the performance of a std function. And on the right, you can see the assembly generated for his example. And the only useful work this assembly does is the highlighted call to some others, which is the wrapped function. And later in his talk, he shows how to remove all that excessive assembly. One of the tricks is visible even on this slide, this extra void star parameter. And actually, to make these optimizations, from this talk, we already have all the necessary knowledge. We need to know about this parameter passing, because std function or zoo function, it's a function object. We need to make sure the parameter's order is consistent, which that extra pointer ensured. And also, we need to use enhanced perfect forwarding, which preserves passing in registers instead of replacing them with references. Okay, now let's look at a different example, also from core guidelines, which say to not pass an array as a single pointer. And they have this example of like range copy, and they recommend to use spans in the end to avoid accessing unrelated memory. Okay, so let's try to do this. But again, we already learned about the parameters order. So if you want to call std memcpi, our function would better have the same order of parameters. So we do this in the raw version. And we do this in the second one as well, but we append, well, we don't use std span because we already saw it has overhead on some platforms. So to separate that part, we emulate the span by just passing pointers and sizes, but we pass an extra size. We pass both source and destination size. And why do we need them? Well, likely we want to assert that they're the same. But we make sure this assert is compiled out because we're not in debug mode. Okay, so for this example, who thinks there's no overhead from this parameter? Nobody. So looks like everyone expects that the second function will have some overhead. But you know what? We compile it, and the function just calls memcpi in all the cases. But again, we need to remember that we need to investigate the call site as well. So again, we declare our functions and just call them on some array. And when we compile this code, we see that everywhere there's an extra instruction. And you can see it here, and I think it totally makes sense because we pass the size twice, and that's what is happening. So for this guideline, well, you need to know that it's not free. And if you use exactly the API proposed by the guidelines with spans and called memcpi internally, it would result in some registers moving around because the order isn't the same. And ideally, we would like for that assert to be extracted from the function body onto the call side so that we don't need to pass extra information inside. Maybe the contracts will help us. I'm not sure. And the last guideline we're going to look at says that we need to keep the number of function arguments low. And it says something about missing abstractions, one responsibility. We're not interested about this part, mainly about performance. So I was trying to find a reasonable example for this, and the one I found was triple product, which takes three-dimensional vectors and computes the volume of a parallelepiped based on them. So it's at least some example that makes mathematical sense. And the wiki article provides a lot of options how it can be computed by swapping the parameters. But again, we remember, if our input is A, B, C, we'd better to consume A and B first and in that order. And also, it's better if their output is also passed as the first parameter, at least on ARM architectures. So we use the last equivalent formula, while commonly people would just take the first one and forget about it. And we'll investigate two options. One is just using all ints everywhere. And again, for the purpose of this talk, I'm limiting myself to integers, but for floating point numbers, the principles are similar. And we have a triple product that takes 9 ints. And the second version, we use a vector class and pass it by reference everywhere. So with just 3 reference parameters. Okay, so first let's take a look at the vector variant. Okay, it looks reasonable, but in the MSVC, we see that we cannot avoid talking about security even in this talk. And there's a good article by Nicolas Frechetta which explains why this thing happens. But we're professionals, so we know what we're doing. So or at least we think that we know what we're doing. So we disable those security checks with this decal spec, and we have something reasonable. Okay. Now going to the first version where we used all ints, we see that it's somewhat more code. But in this case, I don't want to make a claim that it's slower because of that. Because in the first case, you would probably have more others accesses inside the helper functions. Just some things I'd like to highlight here. Well, first of all, we have a lot of moving around, right? Which is kind of a problem that the core guidelines mentioned. So if you have even more parameters, you'll have even more moving. And if you forward the same parameters through 10 layers of abstractions, this will likely be a problem. And the second interesting aspect is that we see SP or RSP usage, which is the register for the stack pointer. And it's used a lot, especially by MSVC. And you might be thinking, okay, we used only primitive types. And we remember that primitive types should be passed in registers. So what happens here? Well, part of the answer is that before calling the first function, we need to preserve some state on the stack. But there's another part to it, which is, again, some quotes from the ABI specification, summed up in the final row, final column of the table we're building. Well, number of registers is limited everywhere. And this number is different on each platform. And interestingly, for ARM, those registers are used both for inputs and outputs. On others, the return value has special registers for them. So you can use this table as a reference, but keep in mind it's only for general purpose registers which store integers and pointers. But for floating point types, we could build a similar table. So going back to the core guideline about keeping the number of function arguments low, I think in general the idea is correct, but how much is low can depend on each use case. So it's better to measure. And now we get to the conclusions. You saw that compilers do pretty unexpected things to our code, but it's not because the compiler is stupid, it's because it has to follow all the specifications and not just the C++ standard. But the compiler explorer is your friend in here to see these unexpected things clearly in the assembly. And C++ core guidelines are actually pretty reasonable from performance point of view, even though they don't talk about performance too much. And the most important guidelines that we can derive from this talk to avoid completely unnecessary function call overhead. First, return by value, then pass trivial types by value, others by reference, follow the rule of zero, or at least make your type trivially copyable. Also, very important, make API consistent, especially if you have long chains of function calls. And when using abstractions, well, it's better to understand their cost on your platform, especially if it's Windows, because as we saw, it has the most weird limitations on the types. So yeah, that's all. Thank you so much for your attention. Yes, questions?
Thank you for the talk, Oleksandr. Throughout your talk, you have been saying that the specification forces the compiler to do this, and what the compiler does is worse than what we expect. That has been one of the takeaways from your talk. Shouldn't we conclude that the specifications are wrong if they force the compilers to do the wrong thing?
Well, I totally agree that I'd be happy to modify them, but changing the API is kind of a difficult process in our world and takes a lot of time, and a lot of people get upset in the process. So ideally, we would fix this, but I'm not sure how.
Regarding keeping the argument consumption in the same order that you pass them in, is that only relevant when your arguments are trivial types that are going to go in registers, or would that also be relevant if I was passing like some const references?
Sure, it's always relevant, because when you pass a reference, it's not your value gets into the register, but the reference itself, like or a pointer. It's stored as an address, and again, it's the same registers as for integer types are used and in the same order. So yes, it's always important. Yes?
It is especially more important because if the compiler puts in the stack the actual object, and then you change the owner, the stack will have to be rearranged too. No, it's more in depth.
Oh, okay.
Right, Ignas Bogdanas. A comment to Eduardo first about ABIs and what you have been talking here. The abbreviation ABI means different things depending on the context. So there's a language ABI, there's a runtime ABI, there's operating system ABI, and there's actually platform ABI. So from that perspective, if you really care about the performance, most probably you will define your own. However, you need to understand the cost of that, basically of the compatibility. If you control everything end-to-end, nothing prevents you to have 16 arguments passed in registers, right? But then don't expect that you will be able to use everything what is available. So the other question is for you. If you could go to slide 151.
Okay.
It's about all this large list of scary instructions. Actually, what you see on the output of the code generator does not necessarily mean that this will be executed on the platform. Moves are mostly inexpensive, right? What you have here, moving registers back and forth, that won't be executed. That will be basically finalized at the rename stage. The other thing is processor doesn't execute instructions, it executes operations, and you need to look into the cost of what that basically translates into. Decoding is not expensive, especially on x86. That's mostly a linear process. That aspect about the stack. First, stack is cached. Second thing, contemporary platforms, even if they show from a code that it deals with stack, it actually doesn't deal with memory at all. So you will get very different performance results if you are, for example, profiling and touching the memory of a stack, and if you are not. Right? Basically, it doesn't live outside of the processing core. So those are deep implementation aspects, and however, those implementation aspects have very, very important impact into the overall performance. So it's not that, basically the statement that I have more assembly instructions on the output, that means worse. No, that's not necessarily true.
But yeah, thank you so much for the clarification. And for this specific example, I think I mentioned that I'm not saying that the performance is worse when comparing them. But at least from the instruction cache perspective, avoiding completely unnecessary instructions that are not useful in any way, that's, I think, is definitely good.
Yes, so you need to look into the context. If you run that once, you probably don't care because that will be renamed. If you run that in a loop which does only moves, probably you care, but then the question of what's the practicality, right? That's a synthetic test. If you do something practical, you will have more expensive instructions which actually are besides the moves, and that will be the cost. Right? The fact that you move some arguments back and forth, that's just the register renaming. That doesn't even get to the execution units, right? So they will be available for the actual work that you will be doing. So that's, well, basically thin balance between what you see on the output and what actually happens on the platform and how that impacts the performance.
Yeah,
Right.
thank you so much.
You.
Okay, one more question.
Yeah, please. That was a really fantastic talk. Thank you. So for the bigger data structures where like taking them apart can be faster, I've certainly observed that with MD-span. So there are times when you're especially if you're in a nested loop and you need to take essentially subviews of the MD-span, there are trade-offs where sometimes instead of calling sub MD-span, you would want to just take apart the MD-span. And so I think there's an important design point there, which is that those kinds of data structures, you need to be able to take them apart sometimes. Like sometimes you need to be able to get the pointer and the number and the integers out, because sometimes it is faster, like you observed. So thank you for making that point.
Yeah, unfortunately, that's not always possible. And yeah, I was breaking up span. It worked on some platforms, but on Windows, this wouldn't help because it allows only like 8 bytes in the register passed. So not sure what to even do there. Yeah, thank you. Yeah, looks like there are no questions. So thank you so much for attending.